Now look at the next field in the header. After the first row, the source port and destination port, there is a next field called as sequence numbers, right? And sequence number is a 32-bit field. So next field is sequence number field. Sequence number, right? So what is sequence number is, in TCP, TCP is a byte stream protocol. Maybe note this point. TCP is a byte stream protocol. So what is byte stream protocol is, every byte that is being sent out is actually counted. So counting every byte is called byte stream. So every byte is counted, and counting every byte means whatever byte that comes from application layer to transport layer, we are going to put a number on that. That is called byte stream, right? And what is the byte stream and packet stream is, network layer, IP is a packet stream. IP is packet stream. Packet stream means every packet is counted. If you remember that in IP there is a number called as identification number. If you remember that IP, that second row, the first part is identification number, right? So in that IP header, identification number is used to count every packet number. But here in TCP, every byte is counted, and the sequence number is nothing but the byte number. Okay. And at data link layer, the protocols like HDLC. HDLC is not in syllabus. It is a protocol which is used at data link layer. HDLC is a bit stream protocol. Bit stream means every bit is counted. So at TCP every byte is counted, and at IP every packet is counted, and at data link layer every bit is counted. So that is the difference between whatever is the granularity of the counting you have taken, that is called bit stream, byte stream, and etc. Java is a byte stream, right? So which means every byte is counted in Java. Okay, now see this. What does this byte stream actually mean is, now if there is a packet, here we call a packet as segment. See, I am using the name segment, packet and frame interchangeably. Packet is a generic name. Segment is the name which is used at transport layer, and datagram is the name which is used at network layer. Here I am using segment. So since we are at transport layer, I am talking about segment. In a segment, there will be header, and now there will be body, and this will be bytes. All the bytes which are present inside the TCP segment, every byte is going to get a number. For example, if this byte is 100, the next byte is 101, the next byte is 102, the next byte is 103, like that. The last byte is, let us assume, 150, right? So from 100 to 150, all the bytes are present in this segment. Then what is the sequence number that I should put in the header is, the sequence number of the first byte which is present in this packet should be kept in the header. So the header has a field called as sequence number field. In this sequence number field, we are going to put the first byte sequence number 100 in the header, right? Understood that? So what is the sequence number? Every byte is numbered because TCP is a byte stream protocol, and then the sequence number of the first byte will be present in the sequence number of the header, right? And now look at the next one. The next field in this is acknowledgement number. Acknowledgement number is when you send a segment to the other side is going to send you an acknowledgement. Acknowledgement number is always what is the sequence number of the byte expected next, which means in this segment, if you are sending the numbers 100 to 150, then the next byte expected will be 151. Therefore, the acknowledgement for this packet will be, acknowledgement number will be 151. Now the question is, how will, see, the first byte sequence number you are going to put here, and you can know the first byte sequence number, but then you cannot know the last byte sequence number. Once you know the last byte sequence number, then you can calculate the acknowledgement number. Acknowledgement number is nothing but last byte sequence number plus 1, simple. But then given the first byte sequence number, how can you calculate the last byte sequence number? So that is the question. Now this is the TCP segment, this is the header, and the first byte sequence number is 100, which is present inside the header, and the last byte sequence number is 150, but then it is not present anywhere. You are supposed to count it and get it, right? And now how can you get this one? So look at the header. there is a field called as header length, therefore you can find out the header length, but then there is no field called as total length. If there would have been a field called total length, you could subtract total length minus header length and you can get the body size, and after getting the body length you can find out the last byte sequence number by adding the first byte sequence number plus that one, the total size. But the problem is in TCP header you don't have any field called as total length like in IP header. In IP header you had a field called as total length, right? So now how will the receiver calculate, given this segment, what is the acknowledgement it should send? Why should it calculate? Because acknowledgement number is the sequence number of the byte expected next. How will it do it? Think about it. So I am saying that there is nothing called as total length which is present inside the TCP packet. Then how will the receiver calculate it? It will be calculated from the IP header only. So every TCP segment will actually travel in a IP datagram. IP datagram is going to have header length field as well as total length field. So from the IP datagram, if total length field is present, from total length if I subtract the header length, then I get the entire body length or the segment length of the total segment, and from that segment length if I subtract the header length, then I get the body length of the TCP segment. Then by using this segment, the first byte sequence number and the size of this segment, then I can calculate everything, isn't it? Okay, we shall see a problem later, but for now understand that sequence number indicate the first byte sequence number in the packet, and then the acknowledgement number indicate the next byte expected by the receiver. Once you send some 100 to 150, other side should send the acknowledgement of 151, which means they have received till 150. So those two fields are used like that. Okay, now let's see more about the sequence number field. I told you that sequence number is a 32-bit field. So with 32-bit field, how many sequence numbers are possible? 0 to 2 power 32 minus 1. So now the problem is, if I always start a connection with the sequence number of 0, which means the first data byte is numbered with 0, then there is a small problem which is going to occur. So I'll just explain that with an example. We have 0 to 2 power 32 sequence numbers. Now let us say this is the timeline, and there is sender, there is receiver here, and assume that you are sending the first segment. In the first segment you have all the data bytes, and the data byte of this is 0. The first sequence number is 0. Therefore what will be sequence number of the packet? Always the sequence number of the packet, which means all the data bytes are going to be present in one segment, and for this entire one segment there will be only one header, and on that one header there will be only one sequence number field. Therefore that sequence number field should contain the sequence number of the first byte. So here the sequence number of the first byte is 0. So when you are sending that packet, if it is 0, which means whatever is the sequence number of the first byte, that is going to be on the segment. Therefore on the segment sequence number is going to be 0. So how many data bytes it contains? Depending on that, let us assume that the data bytes present are 0 to 100, then 99, let us say 99, 0 to 99. Then the data segment will contain 0 to 99 bytes, but the sequence number on the segment will be 0, that is the first byte sequence number. And let us say you are sending many frames like this. The second segment will contain again 100 bytes, and what will be the next sequence number? Sequence number of the first byte of the next segment is 0 to 99 on the first segment, therefore 100 will be there. So sequence number will be equal to 100. Then what is the range? 100 to 199 is the range, right? And likewise, let us say you are sending the next one also, sequence number 200. Let us assume that this segment is lost. This segment is lost, which means this segment is not received by the receiver. Then after some time you will wait for it, and again you retransmit it. Therefore again the segment with sequence number 100 is sent, and let us assume that the connection is closed, which means the sender has sent 3 segments between these two, sender and receiver, and after that the connection is closed. Only 3 segments are sent. Just for the sake of assumption, it is not true, just for the sake of assumption, let's assume that. And now it will be simple for us to analyze this. Now during this connection, what happens is there will be a random initial port number which is chosen from the range I told you, from the range 491522 this is chosen, and let us say it is HTTP server with 80, port number 80, and the IP address is yes and IP address is all. Now how do you identify every segment in this communication is, one is using the source port and source IP, destination port and destination IP, as well as sequence numbers. Using these numbers, every segment will be identified uniquely, right? And now it is closed, and next time, after some time, assume that both sender and receiver, they want to again communicate, and therefore one more time the connection is opened and again the segments are being sent. Now already the connection with port number X is closed. Whenever the process with port number X is closed, next time anyone can use the process with port number X, which means next port number could be, there is a chance that it could be repeated as X. Let us assume that next time also when you have chosen the port number, since X is now available, same X is chosen, and here the port number is still 80, so our port number doesn't change, right? And I told you that even though we are using DHCP, Dynamic Host Configuration Protocol, the IP addresses are not going to change all the time. As long as you are using the internet connection, IP address will not change. Once you stop using the internet connection, they might pull it out and then give you a new IP address. Let us say this is happening immediately and your IP address didn't change. Let us say your IP address is IS only and the destination IP address is IR. These two also didn't change. And assume that for the next time also, if you are using the same sequence number starting from 0, which means sequence number is 0 here and you have sent 0 to 99 bytes, and for the next time sequence number is 100, right? At this time when the second segment is arriving, let us assume that the previous 100 segment which you thought was lost, you thought that it was lost, right? But then let us assume that it is not lost, but it is delayed at some point. Some router is holding that segment, and there are lots of surprises in the networks, right? So it is it is hiding somewhere, and then suddenly it appears. The reason is every packet can be there alive for at least 180 seconds, which means 3 minutes. In today's internet, if you send a packet now, it might appear at the destination after 3 minutes in worst case. Therefore what happens is, let us say after you were thinking that it was lost, but then it suddenly appeared now. So there are two segments with the same sequence number 100, isn't it? And how can you distinguish both of them? Both of them are saying that my IP address is IS and IR. Both of them are saying that my port number is X and 80, and both of them are saying that my sequence numbers are 100 and 100. But actually the data which is carried is different, but then you don't know what is the data you should take in. As a process you should make this decision. It is not done manually, right? Therefore there are two segments with the same port number, with the same IP address, and with the same sequence numbers, right? So you can never identify which one is right. That is the reason we don't always start with 0. So what is the solution to such a problem is, what is the problem here? The packet from the previously closed connection is going to be accepted as a packet from the present connection. That is the problem here. The previously closed connection packets may come late, somewhat late, and now that might be accepted as a packet from the present connection. In order to solve this problem, what you should be doing is, don't start from sequence number 0 always. You try to change it, which means don't always start with a fixed number, you start at a random number. So what happens is, the concept is like this: don't start with 0, start with a random initial sequence number. So initially let us assume you have chosen the sequence number 500, then the sequence number on the first packet will be 500, then the sequence number on the second packet will be 600, sequence number on the third packet will be, let us say, 700, and this 600 packet is delayed, therefore you have again retransmitted the packet 600, right? And this is closed, and next time again you open the same connection, even though the port number, IP address are same, but the sequence number is not going to be same. The reason is we are not going to use the random, same starting sequence number. We are going to use random initial sequence numbers, right? So let us say here the random initial sequence number chosen is 500, and here let's not take 500. If if you choose a random initial sequence number, that might come some other number. So let us say the some other number is 1025. Then what will be the sequence number of the first one? 1025. What about the sequence number of the second packet? 1125. 1125. And what about the sequence number of the third packet? If every packet is going to contain 100 bytes, that is the assumption, sequence number will be 1225. So even if this packet which is having the sequence number 600 arrives late to you, one is containing sequence number 600 and other is containing sequence number 1125. Therefore you can say that this is the packet from the previously closed connection, and you can stop accepting it, right? So how did we solve this problem? By using random initial sequence numbers. But still you could argue that even though you are using random initial sequence numbers, there is a probability that the next time also 500 might turn up. Yes, you are right. But what is that probability? Out of these 2 power 32 numbers, the probability of getting the same number again is 1 by 2 power 32. So which is 0.1234, so on 9 zeros followed by 25. So which is very less. So probability of getting the same number again is less. But then there is a probability of getting the number in such a way that there could be conflicts, which means if there is 500, let us assume, and now next time if you choose there could be 600, then the first packet next time could collide with the second packet in the previous one. Therefore the probability of getting a number in a range that could be significant, which means if you are using this 500, what is the probability that next time when you choose a number that will fall in around plus or minus 1 million numbers, which means in this that is simply mathematics. You can do that probability later. I am just saying that if you choose a number now, one number, what is the probability that you are going to get a number plus or minus 1 million to the 500 next time. So the probability is in this 2 million numbers range out of 2 power 32. So the probability is 2 million divided by 2 power 32, which is also not very high. So the collision probability will be very less if you randomly chose the sequence numbers. What I mean to say is, even if you choose it randomly, the chances of getting a collision next time is comparatively less instead of choosing with 0. We cannot completely solve the problem, but yes, we are able to survive with this, because rarely we get this collision problem after choosing it randomly, right? So the point you should note down is TCP uses random initial sequence numbers, which means initial sequence number is always going to be random. Why? To just stop accepting the packets from previous connection in the present connection, right?